So last time we today we are going to, I think we started talking about maybe this is too dark. So if you remember last time we talked about when this something called the relaxation time approximation, right? Approximation, basically when you have these ions, right, immobile ions, so these electrons when they come under electric field, if you have electric field this way, electrons are negatively charged, right, so they move opposite direction, so under the electric field they experience this force, right, so that means it will experience a acceleration. So that means your velocity is infinitely increasing, so but it doesn't continue because they are going to collide with the ions, so then it comes to relaxation, the velocity becomes zero. So with that approximation we write the total force. So net force you can write as, if you like, net force is mass times acceleration, right? This is Newton's second law. You can write as the total force is what now? It's going to be one force due to the applied electric field. Then we assume this force due to the collision, where there's a momentum change, right? Because initially we have, after acceleration support, it comes to mv momentum, then all of a sudden in this short period of time, tau t, velocity becomes zero. So that means you have this force due to that sudden change in your momentum, we call it as the force. Force is basically change of rate of momentum, right? So we can write that one as, we call this a force due to collision. So that is the total force, right? So under equilibrium, so when it comes to zero, that total we can call this like dp over dt, right? That's total momentum change. So this becomes really zero under, because that comes to zero. This F collision, this is the relaxation time approximation, that is basically this negative delta P due to collision over delta T, but this delta T happens at tau time. So that means I can write this one as mv, so you can write this way, final momentum is zero, right, minus mv before the collision. What's the time? This is basically tau. So that's the relaxation time approximation. That means I can write my, under this equilibrium situation, I can write the total, this becomes zero, right? That's so that means zero equals, you have minus E times E, then this becomes minus mv over tau, please remember that one. So from here you can get the relationship for V. V is given by E tau divided by m negative. So this velocity is still in the opposite direction of E, because even if it is colliding like this, then it direction changes, but overall you have motion in the opposite direction of E. That's why it is negative. Is that clear? So this we call, this is the basically the Drude approximation. It's a relaxation time approximation. So this is basically the average velocity of these electrons under electric field E. This is important equation to remember. V is given by negative E tau divided by m. This is average constant velocity. You can assume all the electrons to move with that constant velocity. That's a big approximation, right? Each electron will have different velocities, but you can have average velocity of each electron with this v. Okay, that's also from this one in mind you can calculate your something called the Trude conductivity. Just imagine if you have a simple, so this is what we are talking about, v is given by E tau over m. So this is so anything. So later you are going to see two different velocities, something called the drift velocity, then that is due to electric field. Then there's another velocity, charge motion, due to something called the diffusion. If you have a larger charge distribution and a smaller charge distribution, always charges will move from higher concentration to lower concentration. That is called the diffusion, right? So there are, when you learn about the semiconductors, you learn about one due to this diffusion current, then there's one due to drift. Drift means under the influence of an electric field. Please remember those two things. That's you will see later. Okay, so now we can derive this conductivity basically using this. If I consider some rectangular box, right, with this cross-sectional area is A, length is L, this has N charge density, that means number of charges per unit volume. So N means per unit volume, please remember. Then I can write the current density. Everybody remember, current density means current per unit area. That's very important thing. So J is written as total current divided by the cross-sectional area. If this is my current is flowing this way, this is my cross-sectional area. Suppose if my current is flowing here to here, then what is the cross-sectional area? This is the normal area, right? So then in this case, I can write what is I? I is basically dq by dt, right? So I can write I as charge this way divided by A. What is A? Oh, I just write as A. What is Q now? You can easily find Q is, we know how much charges in this volume. What is the charge? So N times volume. Volume means L times A, right? So times charge. So that means your Q will be basically E times N times A times L, right? What is A? A times L means what? Volume. Volume times N means total number of charges times each electron has charge of E. Then this will give you the total charge. So now, so if you consider charge moving from here to here, so what is the time from moving from here to here is length over velocity. So that velocity is what we find, this constant velocity, right? So that means I can write this dt for that charge to move from there to here, that is basically L divided by V, right? Is it dq over dt. So then we have A here. So if you do this one, you get I over A. So J, you can write that J equals, here if you do this one, you can say A and A cancel, L and L cancel, then you get, we go upstairs, right? En, that is the current density. This is also something you should remember. So charge times charge carrier density times velocity is the your current density. Please remember, this is basically amperes per meter square, right? Yeah. Current density, not charge density. J means I over A. Is that clear? Okay, then we can plug in this number, then J you can write as En times V is, forget about the sign, so if you get the number you can write as EE tau divided by M. So this will give you N E squared tau over M times E. If you write like this, in actually this we know J is always if electron that you can put that negative sign. This tells you electrons are moving in the opposite direction of the electric field, right? If you have, anybody remember the Ohm's law?
Like current density or
Yeah. So you can write two ways, right? Everybody remember V equals IR. That's one way. Or in the macroscopic way we write as J equals sigma E. So they both are equal. You can easily show, right? Because V is what? Potential difference means V. That's a potential gradient equals E, right? So you can write V as E times some distance, right? Equals I, you can write as basically J over A, right? So then if you put, actually I haven't defined R yet, yeah, that's, I'll show you after I define R. Right now just remember Ohm's law, you can write either, this is everybody remember, right? V equals IR. So O, J, these are identical, these are equivalent to expressions. Now you can say here J, E, then what is this? Basically sigma, right? So that means you can say for a metal, your conductivity, we call this sigma, is clear, right? Because this J, this is E, then this part is sigma. That basically N E squared tau over N. This is very important expression. This will give you the electrical conductivity. So you can see if the number of charges are more, you get higher electrical conductivity. Also if the mass is smaller, it can respond faster, right? So tau is the relaxation time. So if the tau is large means what? Tau is large means you have this longer free path, right? So that means your conductivity is higher. Because tau is given as your gamma divided by your velocity, right? So if you have some impurities, your tau is going to be smaller. So this is called a very important content called Drude conductivity. Drude conductivity. So tau is that relaxation time. So this is, so this maybe somebody is doing this very sophisticated like quantum systems and things like that. So still you can get rough estimate for the electrical conductivity using this equation. So that's really simple situation. So yeah. So then sometimes we define this is the conductivity, right? Conductivity. So we define resistivity, that is basically 1 over sigma. But this is, I'm going to show this is not that simple. Because ideally, and next we are going to talk about this one, sigma and rho are really some tensors. So that means sigma can have some component like sigma x, say if two-dimensional you can have sigma xy, sigma yx, sigma yy, right? Say like a matrix. So then rho is really what? Inverse matrix of this one. You know how to find the inverse of this one, right? How the inverse? You have to divide by the determinant. So then you have this, what's called the adjoint, right? So this becomes like negative, sorry, sigma yy, they are changing here, right? Then this one become negative sigma xy and negative sigma yx. That's how you get raw things, right? But in general, for bulk material, you can say resistivity is inverse of the conductivity. So then also we define in 3 dimension, we define resistance as, if you have this is A, this is L. We define resistance as rho times L over this cross-sectional area A. So, but this is going to be a little complicated if you go to low dimensions. Suppose if you have 2 dimensions, how do you define that one? You don't have thickness, right? So later I will talk about this. So typically people define R and rho has relationship. R is going something like rho times L, this dimensionality. You can see in 3 dimension, this is 3 minus 2 is 1, right? So that means rho times L. So that's true because this has, so other way, right? So rho equals R times, yeah. So if D equals 3, this becomes 1, right? R times length. So that's true, right? Rho equals, because here you have width and thickness, one length dimension cancel, then you get 1, right? But if you have 2 dimension, what happens? This is 1, right? That means R, rho and R are same. Just remember, so probably you might not see that. In the 2-dimensional case, resistivity and resistance are, they have the same meaning. So later we'll talk about that one. But yeah.
What do you represent the conductivity in their tensor forms?
So there's something called the sheet resistance. So yeah, so that we don't think about the width. Yeah. So these are details. So for the time being, just remember, if you have a conductivity, to get the resistivity, basically it's the inverse of conductivity. So now let's look at how this electrical resistance changes with temperature. So we know in a metal with temperature what happens? Always your resistance increases. That means conductivity always decreases, right? If you take a metal, this is very important. So temperature versus say rho or resistance. So we know if you take a metal and heat, your resistance is always linearly increasing, right? That means conductivity is decreasing. Why is that? That's very important. So in metals, your conductivity is mostly determined by the collision or the scattering of these electrons from ions or maybe other impurities. But semiconductors is opposite. If you increase your temperature, you are changing your carriers. But in metals, already you have so much charge carriers, right? It's like in the ocean, if you put one few drops of water, it doesn't make any difference, right? So that means N has no effect in metals. But semiconductors, they have very little charges, but if you put or take out some charges, that will really change your conductivity. For metals, it doesn't matter where, this is so large, right? Free electrons. So then what determines the resistivity? Only tau, right? Because if you have more, electrons are moving, so these are the immobile charges. If you increase temperature, what will happen? These also try to vibrate more, right? So if it is, suppose electron is coming like this, So now it is going to collide with this one, right? But if it is coming like this, they just pass by. Now suppose you are heating it to high temperature. We know phonons, right? Electrons are, the ions are vibrating. Then these electrons can collide more, right? Because previously suppose it is going without getting scattered. Now since it is, so then they get collided, right? So that means you have more scattering, high temperature. More scattering means your tau is going to be smaller, right? So that means sigma is going to be smaller. That means rho is going to be larger. So that's what happens. So yeah, so actually I have that one here. So if you can consider tau, actually tau is basically gamma over V. So gamma is the one going to get affected by, V is not that different. Yeah. That's what, so the relaxation time is mostly in for metals, tau determines the conductivity. Yeah, we already talked about this one. So one important thing is, if you talk about these even the collisions, mostly the electrons closer to this EF, only they have enough influence on the conductivity. The things away from this one, because they have constant velocities and constant energies, only the ones close to this one, they can be contributing to the conduction. Please remember, in any metal, only the electrons with energies close to the firm energy will contribute to the electrical conductivity, not the ones away from this one. That's what this says. So even this average velocity, because tau really depends on gamma over V, right? So this V doesn't change for these things because they are low energies anyway, right? Already it's filled. So, but once here, they can have some change in your V. Please remember, this is the important thing. Only electrons near EF contribute to the electrical conductivity. That makes sense, right? So before this one, so then we can easily argue, if you take this is the one I was trying to explain to you. So if you look at, actually we already discussed that one, right? If the temperature is high, your cross-sectional area becomes higher, right? Because, yeah, moving, so that means this cross-sectional area is proportional to x squared, right? So if you look at the thermal energy, your potential energy is half k squared, so that's proportional to temperature, right? If the temperature is higher, your cross-sectional area higher. That's, you can easily show from this one, right? That's why if your temperature is higher, your cross-sectional area is higher. That means your resistivity is more. Velocity doesn't have, yeah, because mean free path is smaller, right? That's why V becomes smaller. So that means rho is proportional to T. Is that it? So please remember, metal conductivity is totally determined by tau, not by N, because N is already so large. So the tau depends on the collisions, right? So if you have high temperature, you get more collisions. Okay, so before we go to the next one, actually, you can see some of these resistivity of rho as a function of T. You can see very linear, right? Also, that's small. The thermal, the resistivity is very small. Conductivity is very high for metals, right? So then at low, what happens here? They come to zero with some saturation here. Anybody has any idea why? Any metal has some impurity, right? You cannot have perfectly pure metal. So that means eventually it doesn't come to zero. Ideally at 0 Kelvin, you should have zero resistivity, right? But it always has some impurity, that's why It's just saturate to that value, not 0. People have shown that one by purposely adding impurities. When you add impurities, you can see your resistivity, even initial resistivity is increasing because you are putting more impurities, right? So then it saturates at higher level because that's the residual resistance, right? Here you can see initially you have, but that also saturates at these parts are linear but saturates at lower resistances. Okay, so far we were talking about this electrical conduction in real space, right? Now let's look at what happens in the reciprocal space. So if you think about the reciprocal space, what you have here is in K space, right? You have this Kf Fermi vector. That means all the states here are occupied. All the states here, they are unoccupied. This is a K space picture. Then in the energy space, this is basically, this one means you have Fermi energy. These are the field state that corresponds to this part, right? Field state. These are the unoccupied, the empty state. You can see the two pictures, right? Energy picture and the momentum, K-space picture. Is that clear? So now just imagine if you have an electric field, so that means it has a force given by this much, right? So then the force is given by so if you know the force, then you can calculate your momentum. So what is the momentum? Delta P over delta T, right? Change in your momentum. Let me show it here. Also, we know the momentum for, if you consider the electron as a wave, so that's how we got K, right? We have the traveling waves. So what is the momentum for a wave? De Broglie wavelength, H cross K, right? Everybody remember this? In particle picture, P is mv. In the wave picture, P is H cross O, P is H over lambda, right? Same thing, De Broglie wavelength. So these two are the same, right? H becomes H cross, lambda becomes K, 2 pi over K, right? So now, if you consider this one, so then I can write delta P as H cross delta K, right? So that's what this one, H cross delta P is H cross delta K. Also I can write delta P as mv, say after collision is 0, that means mv minus 0. Is this clear? So then also if you remember the velocity function we wrote, we wrote as E tau over m, right? So now I can write m times v means what? E tau. So if you get this, is that clear? So that means I can write my delta kx as this value, delta px over h cross, that is mvx over h cross, that is, this is, so this is my delta kx, if you plug in this number, right? So what does this mean? So this means because of this, so this is k vector, right? So because of this electric field, your k vector is changing, right? Suppose if you had some k value here, so after that time tau, that k vector is going to be slightly different. That means it becomes negative number. That means this the Fermi sphere, that's going to be shifted like this in the negative. Suppose electric field is in this direction, so this is going to be shifted by delta K, right? So here you can see by this much. So if you look at this one, you can see this was the one before. After electric field, it moved negative delta K, but that value is what? Delta K given by this value. Is that clear? So now, if you take this symmetric sphere, so for every positive K, you have a negative K, right? Here also positive, here we have, because it's symmetry. That means you don't have any contribution from the electrons here, because you have positive, negative, right? But if that moves this way, you can see in this overlap region, so there's no contribution. But how about this small unoverlap region? That K, delta K can contribute to the current. That's the picture in the K space. This delta K is given by this value, right? That's the influence of the electric field. So that is same as this one. So that means, what does that mean? So these are the K values. This is your Kf, right? Remember, this is my Kf. So this means in the energy picture, that is EF here, right? The ones closer to this one, sorry, that's the one contribute to the conduction. That means this becomes this part. You can see how from EF promoting to states above that one, just like that. Here states from K, they are changed by this small delta K. Not any K values from here, because they are cancelling each other, right? But the ones this closer to the Kf, that means closer to EF, they are the electrons contribute to the current. That's why sometimes when you do this complicated theory, people calculate all these properties in the K space. That's much easier. In the real space it's more complicated, but in the K space that becomes much simpler. Okay, so this basically electric conductivity. Yeah. So next I want to talk about this different thing called the Hall effect. This is also a really important phenomena. So if, like, especially, so if you take metals, your charge carriers are electrons, right? So that means there's no issue. You find the carrier type, that always you get negative carrier type, right? But if you have a semiconductor, so we are going to talk later, there are something called intrinsic semiconductors, right? So they have, so there's something called electrons and holes. So intrinsic means they have same number of holes and electrons, but we can purposely do something called the doping. This, you can put more holes, then we make it like p-type material, or we can put more negative charges to make it n-type material, right? That's the key thing for all the semiconductor industry, right? To use the, we call the p-n junctions. So intrinsic semiconductors has no interest, right? They are pretty unfunctional. But if you can make it p or n-type, that makes the useful devices, solar cells, or the light emitting diodes or transistors, everything coming from the p and n. So when you have this kind of p or n material, so Hall measurement is the easiest and most direct method to quickly test whether it's p or n type. So that's why Hall effect is so useful to identify the carrier type and also the carrier concentration, n. Remember, n for, so typically p for the holes and the p-type materials. So let's see what this whole concept is. Basically, Hall if you take say some cube like this, if I connect this one from these two ends to a voltmeter and apply some electric field, suppose I apply my electric field in this direction. So then if I have electrons will always flow in the opposite direction, right? When electrons are flowing this way because of this current is flowing from this surface to this surface. To measure the whole effect, I have to apply magnetic field normal to that surface. So now you have electron flowing this way, then I have magnetic field. Then what will happen? So the electric field is this way, right? Everybody remember the Lorentz force? So if you have a charge, if you have electric field, you get a force given by E times E, right? Is that clear? If you have a magnetic field, what will happen? It will experience something called the Lorentz force, that is given by is E times V cross B. V is the motion of the electron, B is the magnetic field. If the electron is not moving, that means V is 0, there is no force. But if you have electric field, electron moving, if I apply magnetic field, it will experience this force given by V cross E times V cross B. Now in this one, suppose I have electron flowing like this. Now I apply magnetic field this way. So which direction is the magnetic force? V cross B, everybody remember right hand rule. So V is this way. Then I have to curve it towards B. Then my force would be in this direction, right? So that means electrons were going like this, that will turn towards the surface, right? This V electron flow is, but now we have to be very careful. Electron was moving this way, magnetic field this way, then the force is this way, but electron has negative charge. Then the force should be which way? Opposite direction. That means it was moving like this, it will curve towards this face. That means it was moving like this, it will turn towards this face, right? That means electrons will accumulate on this face. Then this part becomes positive, this part becomes negative. So if you keep doing this, what will happen? Always charge negative electrons will accumulate here, this part becomes positive. So that cannot happen continuously, right? Then what happens is eventually the system will apply opposing field so that it cannot accumulate any more electrons. So that is called the Hall field or Hall voltage. Is that clear? So yes, what happens here? So this is how the electron moving this way means your conventional current is this way, right? That's clear. So that means you can, if I draw this one, so this is what happens. So current is this way, that means if I connect to a power supply, my positive terminal is connected here, right? Negative terminal is here. That makes conventional current this way means electrons are moving in opposite direction. V cross B this way, but when you consider the negative charge, it will accumulate here. Negative charges will accumulate here, positive charge will be on the other side, but the whole field will be to oppose that one, right? Suppose if I have, say this is positive, negative. So now if I have negative charge, suppose if I So we are talking about electrons, right? Electron coming here. So if I have this the field, if the electric field is this way, that's how charges are moving this direction, right? Then the whole field should be opposite direction to cancel further accumulation of charges. Is that clear? Okay, so now we can easily calculate the whole field. So how do we do that? So in this one, we can write first the current. J is what? I over A, right? A is here, W times, suppose this thickness is T, W times, that's the current density, right? So then if you write your total force, the force is given by E times V cross B. What is that one? E times V cross B is what? V times sine 90 in this case. That makes it easy, right? Because V is this way, B is this way, V cross B means sine theta, right? What is that angle? 90. That means this is basically E times V times sine 90. That is 1, right? So this, that's your total force on the electron. So then we know, so this force is going to be, so if this force is there, then charges are going to indefinitely accumulate here. So then it will apply something called a whole field to balance this one. Then it will not accumulate anymore, right? So that means, suppose that field, in this case actually, if you draw this way, so that field is from this surface to this surface, right? Suppose that field we call E whole, EH, or corresponding voltage V whole. So but this is given as W, right? Everybody remember how to connect these two? Potential gradient, potential difference and electric field. We know VH over W is EH, right? So basically your EH is given as VH divided by W. This is basically the definition of electric field, right? Potential gradient. So that means I can write this one. So this is the force on the electron. This is going to be balanced by the whole field, right? What if the whole field is EH? What is the force? E times that whole field. Right. So that you can see E and E cancel, then you get V as this whole field divided by your B. Or if you want to write E H, you can write as VH divided by W. Yeah, VH and EH are connected this way, right? So that is my V. So now I can write my J. J is given as I over WT. Also we know J is given as, if you remember, we showed that is En times V, right? So V also, now we can substitute here, En times V, you can write as VH over W times B. Now if you take this one, you can see W and W cancel. Then what you get is, I can write here VH is given as I times B divided by, you can W cancel, you get En, right? ENT. B goes here, IB divided by, yeah. This is called the hole voltage. Also, we define something called RH. He called the hole coefficient. So that is defined as this whole field divided by that J times your magnetic field. So that means that is basically if you J divided by EH is here. From here we can write that EH you can write as I just want to get, so that will cancel all the things here. So if you do this one, you get this as simply 1 over En. You can easily show this one. Then we have J from here, IOT. So if you look at it, it's shown here. So this is J is, yeah. Actually from here you can easily get right. So this is correct, right? This is the force balanced by the whole, the force due to whole field. So that we showed this one. Then J is NQV, NQVV. This one, then yeah, that's already here, right? Yeah. So then if you take this J divide by EH divided by J times B is 1 over NQ, right? NQOE, whatever. So this is that clear for everybody? So this is definition of this is called the hole coefficient. Is that clear? Or you can directly measure hole voltage from this one. That's very simple. What you do here, take your material, apply some current, then apply perpendicular magnetic field and measure the voltage across that one. So from that you can easily get, you know I, you know the B. So if you measure the thickness here, you can calculate your N. And also that hole voltage directly tells you your carrier type. If you do for electron, N is negative now. Like E is negative, right? So that means this becomes negative. So metals always have negative hole coefficient, except there are few things that is not really negative. In general, metals have negative hole coefficient. Is that clear for everyone?
We did this in our,
What's this?
we did this in our research methods lab.
Yeah, yes. So here, this one. Yeah, then I already showed this one right here. Yeah, this is the one, EH. Yeah, this expression is here. Okay, so now you can see this whole coefficient. People have measured for different metals. You can see sodium, copper, silver, they all are good metals, right? They all have your RH value negative, but this also negative. There are few elements they have actually positive. So anybody has any idea? So these metals actually have this enough, something we are going to talk about later, the holes. So even for the metals you can have holes, so that contribute to the positive the hole coefficient. But other than that, all the metals should have negative hole coefficient. I will later discuss this one. But if you use the field free electron gas, it always gives you negative number, right? So here is something really nice. If you compare some solid materials and their the theory value, so calculating with this one, right? So if you know this carrier density, you can calculate this RH using simple free electron gas. So can you see the solid values are not very close, right? So if you look at, but look at the liquid numbers. So free electron, compare the free electron gas versus this one. You can see, if you consider these things, almost same. So this is liquid state. If you take, say, silver, I just melt it, then measure the Hall coefficient. Here, I just directly measure the solid. If you do that one, you can see they are not very good, right? So even here, this always. Anybody has any idea why do we get better results when you melt it? So what do we eliminate by melting? No crystals, right? When you melt, you don't have any crystal. That means no any like phonons or anything, right? So that means only you have just free electrons there. So no lattice. Because melt means it's not in the lattice, right? It's like gas phase, this liquid phase. So that's why you get perfect agreement with this one. But if you have a solid, you have this crystals, that means you have phonons and all these things. So that can make it complicated. So if you want to make it liquid, no crystals, that means it's perfectly good free electron gas. Okay. So now let me put this, actually when I talk about this rho x and rho y is not very clear, but if you do this way you get the better idea. So this, we talk about Drude conductivity, right? And the Hall coefficient. How do we really measure these two simultaneously? Typically if you have anything, people make this something called this Hall probe. This is how usually we make a device if you want to do. So these are, suppose your material, you use some kind of mask and make, this is your sample. So then what we do is, remember that we talk about Drude conductivity. They are usually we call this longitudinal conductivity. That means you pass a current from here to here. Suppose you apply current here, then you measure the voltage across these two, right? So then if you divide V over I, you got R. That is really this longitudinal conductivity, what you really do in any metal. Can you now tell me, if I want to measure the whole voltage, how do you measure? I can pass the current same way, but I measure the voltage across these two, right? And apply magnetic field perpendicular to that one. So that's how usually when people do the measurements. So, if you don't have this kind of very regular sample, suppose you have something like this, then what people do is they do something called the Van der Pol geometry. You just put 4 contacts like this, then you pass current like this, then measure the voltage like that to get that your resistance. To measure the Hall probe, how do you think it should be? You pass current from here to here, then measure the voltage across this one with magnetic field on like that. Is that clear? So this is called the Van der Pol geometry. This is real Hall probe. So then this is also very important. A lot of people miss these details. So if you think about the conductivity or resistivity, this is also important thing. I said you can write Ohm's law as V equals IR, right? R is related to rho. So that means if this is my independent variable, this is dependent variable, right? If I apply a current and measure voltage, what you are really measuring is R. If I use this one, so this means you are applying a voltage, right? E is related to voltage. If I apply a voltage and measure current, what you are really measuring is conductivity. Please remember, because here you apply current and measure, this is your dependent variable, right? If you apply current and measure V, you are basically measuring resistivity or resistance. If I apply a potential difference and measure current, you measure sigma. So then also, if I do this geometry, suppose my current is going this way. Suppose this is my x direction, right? If I measure voltage also in this direction, right? That resistance or resistivity we call rho xx. What does that mean? Current also in x direction, voltage also in the x direction. In the case of the whole field, we are measuring voltage across, current is same x, but voltage is which direction? Y. That means whole voltage means really, by measuring whole voltage, you are measuring rho x, y. If you say rho xx means you are passing current in x direction, measure the voltage also in the same x direction. Rho xy means you are passing current x direction but measure the voltage in the y direction. But to make this one, you need to have magnetic field, right? Otherwise you don't have xy, because to make charges to move, you need to have magnetic field. You don't get rho xy if magnetic field is 0, right? But rho xx is always there if you have resistance. So please remember these quantities, rho xx and rho xy. So rho xy is basically the whole resistance, right? Because you're measuring in the y direction. Is that clear for everybody? These are some details usually you don't get to see. So here I am doing very general case here. Suppose I have electric field and magnetic field, then I can write my total force. Total force is given by E plus V cross B, right? So in the like CGS unit, usually you divide by C. Don't worry about that one. I just write like this one. So C is not important at this part. So then I can write my, can we write the relaxation time, the equation of motion? How do you write? Total net force is given by basically d by dt, right? So this equals total force is same, negative E, I don't know, whatever if it is, E plus V cross B. Then you have the momentum, the collision term, right? That is given by the P divided by tau. That's the total equation, right? So then also we know under the equilibrium, this part becomes 0. The 0 equals, this whole thing becomes 0. Is it clear? Now we can write this equation considering, suppose my E is basically has two parts, right? I have EX, EY, because that is only flowing on this direction, nothing in the C direction. Oh, this is 0. Same thing PX, right? P momentum also has PX, Py and 0. What is B? B is 0, 0, B, right? It's only in the C direction. Is that clear for you? So now just solve this equation. What do you get here? What you get is 0 equals E. Then E I can write as Ex plus Exi, right? Plus J times Ey. Then plus V cross B. We have Vx, Vy, 0, right? So now how do you get V cross B? So we know how to get the cross product of two vectors, right? So how do you do that? If I take I, J, K, V is Vx, Vy, 0, B is basically 0, 0, B, right? Now if you do this one, what do you get here? So if you take I, you get Vx, Vy times B, right? This is 0. Then if you take minus J, what do you get? Vx times B, J. This is 0, right? What is that next term? K term is 0. You get only 2 terms from there, right? Is that clear? Everybody good with this? This B cross B. This simply. So then how about the next term? Minus P over tau. That means that also I Px over tau plus J Py over tau. That's it, right? Is it clear for everybody? So now separate i's and j's. If I take I get E times Ex. Then I have here Vy, B times E. So then I have Px over tau. Is that clear? So I'll tell what is omega C. So then J, if you take E times Ey, then I have next J term, other J term is this Vxb, right? Vxb. So I take that one. Then I have Py over C. Is that clear? 2 equations. So here, since I have this V and here I have E, then I have V, then I have B, right? So we can write V as P over M, right? Vx means Px over M. So this EB over M, this has a special name called cyclotron frequency. EB over M. In this one is usually EB over MC. Don't forget about that C. This is very important function called the cyclotron frequency, given by EB over M. You can easily show this one. If you have a perpendicular magnetic field, your the force is going to be EVB, right? So that should be equal to, if you can, if cyclotron orbit means it's going in a circular. So then you have centripetal force given by mass times V squared over R. From here you can calculate your V as EB over M, right? So then you can relate it to omega. So we have R here, V equals EB over R here, right? Yeah, V equals ER over EB, sorry, EBR, yeah, EBR over M. What is V over R means? Omega, right? Omega is V equals omega R. Oh, just right here. And that's fine, right? Yeah, V equals omega R. If you plug in that one, you get this one. That's basically. If you have any electron going with some velocity V, if you apply magnetic field, it will make this cyclotron orbits, right? So that cyclotron orbit frequency is given by EB over M. That's basically. We replace that EB over M term by this omega. Ideally, it is EB over M. This C is, don't worry about that one. Okay, now we have these two equations, right? So now if I multiply everything by this number and apply J equals this one, then you will get, and also we know sigma 0, that's the total conductivity. So then you can get this relationship. So all these things are there, right? P over these things, we can replace this one. Please do this one here. Is it clear how to do this one? So these two equations, I just multiply everything by this one, then substitute J as wherever P over M, I just substitute by J, then wherever you have this one, replace by sigma 0. So these are the two equations. So now can you tell me how do I get Hall coefficient from this one? This is general. Hall coefficient means your J, Y should be what? 0, right? Because we have to stop that further flow, right? Electrons are moving, then we have this one, but because of the Hall field, that Jy becomes 0. So that means if I make Jy 0 here, then I can get my Ey equals this one. So now what is this one? E and J. J is in the X direction, E is in the Y direction. Then what is that? That is Hall voltage, right? Rho xy. So if you do that one, you get that is as the Hall coefficient. Please remember this. The Hall means current in X direction, voltage is in the Y direction. That's very general way of doing that one. Everybody should understand this is one thing, right? You have electric field and magnetic field. So by combining both forces and using that whole field, right? So you can calculate your. So please everywhere C you can neglect it. And this is CGS unit. Is this clear for everybody? So then also, if you want to, let me go to this one. Then we have time. So if you want to, like I said before, so this is the two equations we were talking about, right? So if you are using this relationship, what you are really measuring is you apply current and measuring E, you are calculating rho, right? Rho, you can have all these things. Then you can write E as this way. Is that it? This E is given by, the rho is a tensor now. This one. So also we know how EXEY, right? From here, EXEY. If you do this one, you can see this function is basically this one, right? One knows it. This function is rho xy. Now, if you look at this one, you can immediately tell. So this is rho xx, right? So rho xx means 1 over sigma. Then this is rho xy. These two are equal. This is, you know, that's the opposite one. From here, you can directly tell rho xx means really that inverse of your total conductivity, n squared tau over m. Rho xy means is h over n c. Right? Now somebody might think if my rho xx is 0, sigma xx should be infinite, right? That's what you naturally think. But we know that's not the case because sigma is really inverse of rho tensor. If you calculate that one, you know how to do the like I said, the inverse of the matrix. Now you can see even if rho xx is 0, sigma xx in this case, if you divide by rho xx, no, yeah, in that case this becomes 0, but rho xy, rho xx, yeah, if rho xx is 0, your sigma xx is 0, but sigma xy is not 0, right? Okay, understand that? So it's, if rho xx is 0, definitely sigma xx is 0, but if rho xx is 0, sigma xy is not 0. So this is the origin of, I don't know whether you are familiar, something called the quantum Hall effect. In the quantum Hall effect, what happens is, so like this is the one I want to talk to you, right? This is how you measure the Hall voltage. You can see current is passing this way, voltages are measuring across this one, right, with the magnetic field. So if you look at your low magnetic fields, so what we were trying to explain is, in low magnetic fields what happens, you have the sigma xy is given by this sigma 0, that is the Bruder conductivity, Ne squared over, sorry, Ne squared tau over m, right? So sigma xy is basically, or rho xy if I write, rho xy is given by that minus 1 over Ne, right? The whole voltage, things like that. So that means if you look at your low magnetic field, if I draw my B versus, actually if I draw, yeah, then also we have B function here, right? Remember we, yeah. So rho h is given by, yeah, Ne. H means B here. So if you draw this one, what do you get? Your sigma xy, rho xx. Yeah. So what did I write? This is xx, right? So Bruder conductivity means xx. So that means one is constant, right? How about the rho xy? That's linear. With the magnetic field, this is what you expect for low magnetic fields here. So this is Ne squared over tau, this whole thing, this is your one big difference. But if you go to very high magnetic fields, so there's something called, so if I have time I'll tell you, this is something called the Shubnikov-Lihas oscillations. So at high magnetic fields, they're starting to oscillate. Actually, this is because of that Fermi sphere is getting distorted. So that is fine, right? So that is really still the classical behavior, because this is still B behavior. This is simply that constant one, but high magnetic field, they have this some modification of the Fermi sphere. But few years ago, right, people found really interesting phenomena that they saw in this two-dimensional electron gas. When you put gallium arsenide, aluminum gallium arsenide heterostructures, there is a electron gas at the interface that's perfectly two-dimensional. So this graphene and all this material came. So this was the only two-dimensional system people could play with. But to get that one, you have to go to really low temperature, and to make the device, you have to have this expensive molecular beam epitaxy. But right now, you can show these properties with graphene at even not that low temperatures. So in a quantum Hall effect, what they found was this, whatever these oscillations are there for rho xx, but whenever this becomes 0, here you can see, then there's a step in the rho xy. The rho xy is supposed to be this one, right? Just like this one. But they started showing these nice steps. So actually, they found that the rho is going something like this. If you look at this rho xy is given by, this is a quantum effect, right? HO E squared is a very special quantity times 1 over, we call this the order of this whole plateaus. So that is given as, this 1 over nu is given as this, still it has the this one, but it goes like some function 1 over n, or sometimes we can call this one I. That's the order of that plateau. You can see when that n is smaller, that rho xy is larger, right? So that means this n equals 1, you saw that large value, but that's completely flat the rho xy value. During that time your rho xx is completely 0. Then immediately when this one starts showing this kind of oscillation going down, and happens at n equals 2, like this. So then again during that time your rho xx is 0, then again it comes down to like, you started showing this really interesting, this whole plateaus. So this I is going from this, that is the n value. So also it was very easy to calculate this very fundamental, this quantum unit of HO E squared. So after they got the Nobel Prize for discovery of this one. So after a few years they found this nu doesn't have to be integer. Even this fractional numbers, see 1 over third. So you can see even 1 over third. So any time if you have this plateau, this rho xx value is 0, then starting to have this peak, then it becomes here. You can see they started seeing all these fractions. You can see these are really difficult measurements to do, right? These are like millikelvin temperatures and very high magnetic field, 30 Tesla. We don't have access. You have to do in a national magnetic lab or something. High magnetic fields and extremely low temperatures, you can do this kind of experiments. So these are some extreme of this whole effect that we were talking about, right? Okay, so I need another maybe 10 minutes in the next class to finish this one. Okay, I'll stop here. So no homework this week, so you can enjoy your fall break and